Hello. Bilal, can you hear me?
Yeah.
Right. Last time we started with the P block and we finished boron family. Yes? Yes or no?
Yeah.
And today we'll start with the carbon family. Okay. Bilal, can you hear me?
Yeah.
Okay, fine. Perfect. So I'm starting with the carbon family. Oh, just a minute, please. Let me. Yeah. Can you see my screen?
Yeah.
I'm now starting with this carbon family. In this carbon family, we have elements like carbon, silicon, germanium, tin, lead. Atomic numbers 6, 14, 32, 50, 82. Right? And if you write electronic configuration, you have now 1s2, 2s2, 2p2. Neon complete, 3s2, 3p2. Argon complete, 4s2, 3d10, 4p2. You know how to write electronic configuration?
Yeah.
Right. So this is the electronic configuration. Xenon complete, 6s2, 5d10. Here we have 4f14 also, then 6p2. And from this electronic configuration, you can see they have general electronic configuration ns2 np2, outermost subshell. Outermost shell has s and p electron with ns2 np2. Okay, got it.
Yeah.
Now from this electronic configuration, can you tell me of how does the atomic size vary down the group?
Larger than the group
Yeah, it increases as you go down the group, right? Why it increases?
because more shells.
Because of increasing number of shells, right? At every step, we can find that number of shells are increasing, which dominate over the increase in nuclear charge, right? Because of the screening effect. Inner shell causes the screening effect. So atomic size increases as you go down the group. Okay. So how about the enthalpy of ionization or ionization energy? How will it
Decreases
vary down the group? Yeah, it will decrease as you go down the group. Why will it decrease?
because more electrons.
No. Actually, what happens? Can you tell me what is enthalpy of ionization? How do you define ionization enthalpy?
Enthalpy of ionization is the amount of energy uh, an electron can lose from its ground state.
Yeah, energy required to eject out electrons, right? Energy that is required. So that depends upon the electron and nucleus distance here, right? This force of attraction, the outermost electron in a nucleus, is directly proportional to charge on the nucleus, charge on the electron upon r square. As the r increases, as the distance increases, the atomic size increases, the force of attraction between the two decreases. Right? If the attraction decreases, ejection becomes easy. And that is why now we need less amount of energy to eject out electron. Right?
Yeah.
This is how the enthalpy of ionization vary down the group. Now, next is the electropositive character. Can you tell me what do you mean by the word electropositive character?
Ionic, positive ion character.
Tendency of a metal, tendency of an element to lose electrons is called electropositive character. Tendency of an element to lose electrons is called electropositive character. Right? Tendency to lose electron is called electropositive character. So, what do you find? How easily it gives electron? That will be the electropositive character, and it is also called as a metallic character. So, what happens as you go down the group? Can you tell me how will the electropositive character vary down the group?
Increase.
Why?
Because enthalpy
Could you please repeat?
decreasing. So
Yeah. Atomic size increases. With this, the enthalpy of ionization decreases. Right? So,
yeah.
ejection becomes easy. We require less amount of energy. So, the electropositive character increases. Am I clear?
Yeah.
Now, next, I'm talking about the oxidation states. How does the oxidation state vary down the group? Can you tell me what do you mean by the word oxidation state?
Um, how many electrons an atom can lose or gain?
Yeah. So, like in the carbon family, if we see this electronic configuration, how many electrons are present in the outermost shell?
4.
So it can lose 4 electrons. You can see if I write the so can you count the number of electron outermost shell? Can you count out? Like what is the oxidation number of carbon here?
4.
4. So the oxidation number of the carbon is equal to 4. Reason being that they have 4 electrons in the outermost shell. Reason being they have 4 electrons in their outermost shell. Right? They can lose only 4 electrons. But as you go down the group, carbon, silicon, germanium, tin, and lead, these two elements can show +2 also. Like the carbon form carbon tetrachloride, oxidation state +4. Silicon form SiCl4, it shows +4. GeCl4, it shows +4. But tin shows SnCl2 as well as SnCl4. PbCl2 or PbCl4. So here it can show +2 as well as +4, both. +2 and +4 both. And we find that the +2 state is more stable as compared to +4. Now question arises here, why so? Why +2 is more stable as compared to +4? Can you tell me any reason that we had discussed the boron family also?
Because it's easier to.
No, there is a particular reason for this. I tell you what, here in this case we have a D and F subshell. This D and F subshell are large and diffused. Are you getting from these words any particular reason you can come to conclusion now? Okay, this D and F subshell, you're not getting me. This D and F subshell, these are large and diffused, bigger size. They can go out, right? Nuclear charge can go out and pull the outer electron inside. And due to which what happens here, this S pair of electron, this S pair electron, they go inside. They are no more available. They're no more available in the outermost shell to take part in bonding.
Yeah.
Right? They're no more available to take part in bonding. So only two electrons are present in the outermost shell to take part in bonding, right? Only two electrons are present in the outermost shell to take part in bonding. So that is why they can show +2 only, not +4. So that is why they can lose only two electrons. They show +2 only, not +4. Okay. This is called as the
Yeah.
inert pair effect. The pair of electrons become inert. They are no more available for making bonding, right? Because they are pulled inside. They are no more available for making any bond. This is called as the inert pair effect. Getting me?
Yeah.
No. Next. Now, carbon in its +4 state, what do you think it will make? Covalent compound or ionic compound? If you make any compound of carbon here, like carbon tetrachloride, where the oxygen state is +4,
Yeah.
so what type of compound it is?
Covalent.
4. What type of compound it is? Covalent or ionic? Only this thing.
Sorry, ionic.
Covalent or ionic?
Ionic.
If you draw the structure, draw it like this, right? What type of bond is between the carbon and chlorine here?
Ionic.
Yeah. No, it is a covalent bond. It's a covalent bond. Remember, there is a Fazan rule. Carbon with a 4 positive ion is very, very small, right? So chloride is bigger. Because of small size, the Fazan rule says, remember the Fazan rule chemical bonding? Smaller the cation, more the polarizing power and more the covalency. Smaller the size, more the polarizing power and more the covalency. So here it forms the covalent compound. Most of the element in the carbon family in its +4 state, they form covalent compound, right? But if you see
Yeah.
here, SnCl2 and SnCl4, right? It's the SN4 positive here and SN2 positive here. It's comparatively bigger, so it forms covalent compound. It forms ionic compound, but it forms covalent compound. The element in its +4 state shows covalent compound, and the +2 state it shows ionic compound,
Yeah.
right? Okay. Next is reducing character. Can you tell me what is this reducing character? Yeah, can you tell me what is the meaning of the word reducing agent here?
Yeah.
Yeah, tell me.
Reducing agent is the chemical in the reaction, the substance in the reaction that causes the reactant to get reduced.
Any element that gives electron and the other element will gain electron. Gain of electron is called as a reduction. So any substance that gives electron for the reduction is known as a reducing element, right? So so any element which gives electron is a reducing agent here. As you go down the group, atomic size, tell me, in the carbon family, as you go down the group, atomic size
Decrease.
increases. Enthalpy of ionization decreases.
Decreases.
So tendency to lose electron increases. So reducing character in- increases. So as you go down the group, reducing character increases. Understood?
Yeah.
Now, next topic I'm discussing is tendency to form p pi p pi bond. Do you know what is this p pi bond? Do you know what is p pi bond?
No.
Okay, tell me what is the name of this compound that I have drawn right now?
C2H4.
No, name of the compound. You're just telling me the formula only.
Butane.
Uh, how many carbon atoms are there?
2.
Two. So what is the name of the compound?
Ethylene.
Ethene. Right. Can you tell me what is the hybridization of this carbon atom? What is the hybridization of this carbon atom?
P2.
sp2. Good. In case it is a sp2, I can make a geometry that is a trigonal planar, right? Right.
Yeah.
Another carbon here. It's a sp2 with the sp2 head-to-head overlapping form a sigma bond, and they are overlapping with the hydrogen here, s orbital with the sp2 forming a sigma bond. And now what will happen with this? It forms a pi bond. Side with the overlapping forms a pi bond. Right? This is called as a pi bond. Right?
Yeah.
So they form p pi bonding. Carbon can make p pi bonding, but silicon cannot make. Carbon, other element cannot make, because as you go down the group, the size increases. As the size increases, the area of overlapping will decrease, and that is a weak bond will be formed. That is why as you go down the group, as you go down the group, what will happen? The bonding p pi bonding will decrease. Only carbon makes p pi bonding, not any other element. Now I'm talking about next one. Tendency to form d pi p pi bonding. Now I'm talking about d pi p pi bonding. Here the d orbital will be used, right? So here I'll go into detail of this. Here I have molecule of ammonia, and it is sp3 hybridized orbital, and it is a tetrahedral geometry, pyramidal shape. Okay, getting me?
Yeah.
Similarly, if I replace here hydrogen with a methyl group, that will also be having the same type of geometry, sp3 hybridization. But if I talk about like this, this is not a trisilylamine. Trisilylamine. This is trimethylamine. This is a trisilylamine. This compound is not pyramidal, but it is a trigonal planar, and with a double bond character. With a double bond character, right? With a double bond character. And now here, what happens? How double bond is formed? Silicon has empty d orbitals. Silicon has empty d orbitals. Okay, the silicon. and nitrogen has p orbital that is filled in the lone pair. So while making this bond, they can give a back bonding. We call it say d pi p pi back bonding. With all the three silicon atoms, and that is why the shape becomes now planar, trigonal planar.
Yeah.
Now we discuss about reactivity with oxygen. They combine to form dioxide. Carbon plus oxygen, they form carbon dioxide. Silicon plus oxygen, it forms silicon dioxide. Germanium dioxide. Lead dioxide. Before that, tin oxide also. They form dioxides. The important feature of this is carbon dioxide is acidic in nature. Silicon dioxide is less acidic. These are, this is even lesser acidic. Germanium dioxide is lesser acidic. But these two elements, oxides, are amphoteric in nature. Can you tell me what is the meaning of the word amphoteric?
Can act as base and acid both.
Yes. It can act as an acid as well as a base. So, carbon dioxide, whenever dissolved in water, it forms carbonic acid, H2CO3. This is called a carbonic acid. Silicon dioxide, when react to the water, it forms silicic acid. Silicic acid. Okay. This carbon dioxide is acidic in nature. If it is acidic in nature, it will combine with the base like sodium hydroxide and forms here Na2CO3 plus water, plus water. Na2CO3 plus water. So you can see salt is formed when acid combined with the base. When acid combined with base. Right. Similarly, silicon dioxide when combined with the base, it forms Na2SiO3 plus water, right? It's a base. This is acid. So acid and a base combine to form salt. Again, I'm proving here that silicon dioxide is acid here. Note it down. Yes or no?
Yeah.
Now, if I talk about this tin oxide, I told you that it is acidic as well as basic in nature. With base, I'm reacting it with base NaOH. It forms sodium stannate Na2SNO3 plus water. Here it is a sodium hydroxide is a base, so sodium oxide is an acid. But the same tin oxide, when react to the HCl, it will form SnCl4 plus water. This salt is formed. We know that acid, HCl is an acid. It means this is a base. So with base it is acid, with acid it is base, and that is why we call this is amphoteric. Amphoteric means which act as a acid as well as a base, depending upon the other element what it is that. Okay, note it down.
Yeah.
Right. Similarly, if we talk about lead oxide, PbO2, with sodium hydroxide, it forms Na2PbO3 plus water, right? It's a base, so it is an acid. Similarly, PbO2 with the HCl, it forms PbCl4 plus water. So it's an acid, so it is a base. So it is amphoteric in nature. Got it now?
Yeah.
Okay. Now we discuss about the halogen derivative, or I can say reaction with halogens. Reaction with halogens. Like carbon combined with the halogen, like chlorine, it forms CCl4. Silicon tetrachloride SaCl4, and so on. Now, question here is carbon tetrachloride cannot be hydrolyzed, but silicon tetrachloride can be easily hydrolyzed. Question here is why. Let us understand the meaning of this question. First, note down the question, then come to the.
Yeah, no.
The carbon tetrachloride, when react with the water, no reaction takes place. This with water, it forms silicic acid. Right? It means silicon tetrachloride can be easily hydrolyzed, but carbon tetrachloride cannot be hydrolyzed. Now let us discuss here why and how.
Yeah.
If you see silicon tetrachloride, SiCl4, with water, the silicon has empty d orbital. In those empty d orbital, silicon gains electrons. HCl is formed and water goes out. So I can say what is hydrolyzed? Hydrolyzed means breaking of the water. H goes with the Cl and OH combines here. This takes place three times more. We can add three water molecule and three moles of the HCl goes out. Understood?
Yeah.
But now question is, if we talk about the carbon tetrachloride here, the carbon does not have any empty d orbital. Carbon does not have any empty d orbital. So when water is formed, water combined, it will not combine. It will not, because carbon does not have d orbital here. Understood?
Yeah.
Right. Now we discuss about anomalous character of carbon. Anomalous character of carbon. Number one, why anomalous means what? Different from the other members of the same group. It shows the different from the other member. Means carbon, silicon, germanium, tin, lead, among all other elements of the carbon family. Carbon shows different property. Question arises here, why and how? The reason is very small size as compared to others. Number two, high electron negativity. Number three, absence of d orbitals. These are three reasons. And one thing more, that is a high enthalpy of ionization. High enthalpy of ionization. Due to these four reasons, it shows anomalous behavior. Anomalous behavior means different from the other members of the same group. Different from other members of the same group. That is the anomalous character. What a reason for this that I have told you. The four reasons. Now we'll apply to the. Now I'll tell you what are those anomalous properties. Now, I'll tell you what are those anomalous properties. Till now, any doubt? Bilal?
No.
No. Number one, anomalous character. Carbon is hard. Rest all are soft. It is a high melting point. Rest all are having low melting point. Carbon can make only four bonds, but other can make six bonds also. Make six bonds also. Only carbon can make p-pi bonding. No other element can make p-pi bonding. Fifth, carbon can show catenation. No other element can show catenation. Can you tell me what is the meaning of the word catenation?
Mhm.
No?
No.
Catenation means self-linking property. Self-linking property. Carbon can make bonding with itself. Mean same type of carbon bonds are possible. Long chain or it may be branch chain. It can be cyclic. It can be benzene ring. Right? It can be any. It can form self-linking property. But as you go down the group here, carbon single bond, silicon single bond, germanium single bond. As you go down the group, the bond length increases. As the length increases, strength will decrease. So the catenation property will decrease. So the catenation property will decrease. So catenation property decreases as you go down the group. Means self-linking property decreases as you go down the group. Understood? Yes or no? Hello?
Yeah.
Are, right. I have stopped sharing for some time. Let me open one assignment. Wait a minute, please. Just a second. Now, I'm sharing my screen with you. Before I share, Belal, can you tell me, are you comfortable with the boron family now? Do you remember what we discussed last time in the boron family?
Yeah.
Okay. I think we did one assignment also last time.
Yeah.
I'll show you that assignment if we have done that. Right? If it done right, we'll not do it. Okay, I'm sharing it. Have you done this assignment? Can you see?
Mm, yeah.
We have done that, right?
Yeah.
Okay. Then we come to this assignment then. Can I see this?
Yeah.
But the cassette is an ore of? Do you know? Cassette is an ore of what? Red on tin. Cassette is an ore of tin. Lead pencil contain what?
Carbon.
Graphite. Butter of tin is. Do you know what is butter of tin?
No.
Okay, wait. SnCl2, SnCl4.5 water molecule. SnCl4.5 water molecule. Write down. SnCl4.5 water molecule. Have you received this assignment from us? Have you received this assignment? Do you have?
No. Wait, let me check.
Yeah. I think it must be with you.
No. No, it's not that.
Okay. Then you note down these points.
Okay.
All the 3 points you noted down.
Yeah.
Okay. Carbon exhibit unique property forming chain of identical atoms called as a, what do you call this property? It is called as a catenation. Catenation is the property of a self-linking property. It means tendency to form identical chain of identical atoms. What about diamond? Diamond is a good conductor or bad conductor of heat and electricity? What do you say?
It's a good conductor.
No, it's a bad conductor. I tell you why. Because in diamond, all electrons are paired. All electrons have made bond like this. Carbon has made bonded with the four other carbon atoms. It does not have any unpaired electrons. No unpaired electrons. Since it does not have any unpaired electron, it does not have any electron for the conduction, because conduction is the flow of electron, flow of charge. No flow of electrons. That is why it is an insulator. It's a bad conductor of electricity. Understood?
Yeah.
Wait. Now, the process of slow cooling of the glass is called as a, just a second, annealing. Remember, it is annealing. What happened? Just a minute. I stopped sharing for some time. Yeah, it is called an annealing. Annealing. It is called as annealing. Dash and dash form of the carbon, which are good conductor of electricity. Can you tell me what are the forms of the carbon which are good conductor of electricity? One is the graphite, right? Any other form of the carbon that is a good conductor of electricity? Wait. Gaseous carbon. Write down. It is a gaseous carbon. Wait. What happened? Wait. Wait a minute, please. Yeah. Gaseous carbon.
Yeah.
Tin chloride is a SnCl2 is a strong what? Reducing agent or oxidizing agent? It tend to gain electron, right? So it is a good oxidizing agent. See, tin 2 positive. It tend to lose two more electron to become more stable. So it is a good oxidizing agent. Note down.
Yeah.
A mixture of dashed and dash is obtained when oxalic acid is heated with sulfuric acid. Note down this statement, then I will tell you the answer. What happened? Yeah.
Yeah.
Carbon monoxide. Carbon monoxide. Carbon monoxide and carbon dioxide is obtained when oxalic acid is heated with sulfuric acid. Can you tell me what is the molecular formula of the oxalic acid? No, oxalic acid. Remember, understood? Glass is attacked by hydrofluoric acid. Remember, glass is attacked by hydrofluoric acid. Note it down.
Yeah.
Tin sulfide is soluble in dash ammonium sulfide. Yellow, not yellow. Yeah, just remember it. It's an experimental observation. Carbon monoxide burns with blue flame. Carbon monoxide burns with blue flame. Nickel carbon monoxide forms volatile coordination compound with nickel. It forms, remember, NiCO4. It's a bracket here. Understood?
Yeah.
Now the alkyl substituted chlorosilane gives silicones. I think silicones. Yeah, silicones. Okay. Now
Yeah.
the trialkyl yield here will also give silicon. One OH will be replaced by the OH group. That type of silicon will be obtained. Do you know what is this C60? It is called the Buckminster fullerene. Okay.
Yeah.
The most stable allotropic form of the carbon at a high temperature is which form is most stable here? The diamond. Diamond is most stable here. Jyotish Vishleshwan. Okay. PbCl4 form PbCl4 but does not form PbI4 and what it does not form. Remember it is not forming PbBr4. Then graphite is better lubricant than dash on the earth, which is better lubricant on earth. Better lubricant on the than on the earth. What is the mean? On moon. Because their gravity is less. So the friction will be less.
Yeah.
Formula of the white lead is P4, I think. Yeah, P4. PbCO3. Write down PbCO3 dot PbOH whole twice. PbOH whole twice. This is called the white lead. Just a second, please. Yeah. In drinking soda, carbon dioxide is present under high pressure. Carbon-carbon bond length in diamond is, while carbon-carbon double bond in the graphite is, some values are given. Large and small. Yeah. It is large here. It is small here. In tin chloride reduces nitrobenzene to, remember it is a aniline. Nitrobenzene is this one.
Yeah.
NO2 here, and it get reduced to the NH2. Carbon monoxide is absorbed in a solution of dash under pressure, while carbon dioxide is absorbed in a solution of. It means carbon monoxide and carbon dioxide are soluble in different type of solvent. So what is that? Let us see. Cuprous chloride and KOH. Cuprous chloride, it is Cu2, Cl2 and aqueous potassium hydroxide. You have to remember it. These are all important questions. Dash is the only metal which is used to make a protective shield against radioactive radiation. Lead, radon, Pb. Okay. Carbon dioxide has no dipole moment as it has symmetrical molecule. You can see carbon dioxide is symmetrical molecule. Null vector operates over here, and that is why no dipole moment is there. Okay.
Yeah.
Carbon monoxide combines the chlorine in the presence of sunlight to produce carbon monoxide with the chlorine. What does it produce? It forms phosgene gas that is known as a COCl2. This gas is called as a phosgene. Last part. Carbon plus nitric acid to give carbon dioxide plus. I think NO2 gas is there. Yes, NO2 gas. Complete it. Understood? Understood? Yes or no?
Yeah.
Right. Now, this much we have done. This assignment we are done, right? Okay. Now, any doubt? Ask me now.
No, no.
Okay. Just a second. Do you know what is dry ice?
It frozen carbon.
Yeah. So the carbon dioxide. Dry ice is solid carbon dioxide. It is solid carbon dioxide. It is also called dry cold. DRIKOLD. Dry cold. Now, Bilal, just give me a minute. I'll be back. We are left with the two more important topics to be done. Just revise what we discussed today. I'm just coming back in a minute only. Yes, I'm back. Hello. Hello, can you hear me? Bilal, are you there?
Yeah.
Okay. Now we discuss about just another question, another important topic. If I say I have a compound of SiO2, we call it a silicon dioxide. Have you seen it practically? Have you seen it practically?
Okay.
Hmm? No. Have you seen sand?
Yeah.
Yeah. It's the same as silicon dioxide. And it is solid, right? What about carbon dioxide? What is the physical form of carbon dioxide? Solid, liquid, or gas?
Yeah.
My question is, both these carbon and silicon belong to the same family, same group, but their oxides have a different physical form. Carbon dioxide is a gas, but silicon dioxide is solid. Can you tell me why? Any reason? Any
Mm,
no idea?
no.
No. Okay. So let us discuss here. First of all, carbon dioxide. Let us discuss the shape hybridization of carbon dioxide. Right. In case of the carbon dioxide, this carbon is sp hybridized. In case it is sp hybridized, it will be linear geometry. And these are the two unhybridized orbital of the 2p energy level. And oxygen, it is a two unpaired electron. With one, it will make a sigma bond. With the other, it will make a pi bond. Both of these are the 2p energy level here. They can make effective p pi bonding here. Second oxygen, the same way, and form sigma bond. And here they are overlapping with a pi bond. This one and this one making a pi bond. Right? Oxygen has three orbital here with the pi like lone pair here. They can make all the valency of the carbon is now satisfied. The carbon making double bond, the valency of carbon is satisfied, valency of oxygen is also satisfied. So between two molecules of the carbon dioxide, there is no any interaction possible. In case they have, in case they have high pressure and low temperature, then the gas can be liquefied. Otherwise, at room temperature, Otherwise, at room temperature, this is a gas. Right? This is a gas. Understood. The two molecules exist as a discrete molecule here.
Yeah.
But in case of the silicon dioxide, if the silicon is also sp hybridized like this, like the carbon dioxide, these are of the 3p energy level. With oxygen, it will form a head-to-head overlapping, forming a sigma bond. But oxygen is having this orbital is of the 2p energy level. So this sidewise overlapping is not possible. Pi bond will not be formed. With other oxygen, again, you can see sigma bond is possible, but the sideways overlapping is not possible because this is on the 2p energy level. This is a 3p energy level. So what do they do? This silicon makes sigma bond with the two oxygen, and now their two valencies satisfied are left here, and oxygen has left one more unsatisfied valency. They combine with the more oxygen, sigma bond. They combine with more silicon, making a sigma bond. All the bonds are sigma bond. So you can see that it continues, and it gives rise to three-dimensional network. It gives rise to three-dimensional network, and that is why it becomes solid here. Understood?
Yeah.
So that is why we discuss here that this carbon dioxide is a gas at room temperature, but silicon dioxide it's solid at room temperature. Understood?
Yeah.
Now we discuss the next topic now that is called as the silicones. Right on. Silicones are synthetic, organosilicon, polymers containing repeated R2SiO units held by SiO-Si linkages. SiO-SiO linkages. So let us understand here how are these formed. Noted on the definition?
Yeah.
Right. Let us now understand here how are these formed. Two molecules of the chloromethane. Chloromethane is this one. Is treated with the silicon in the presence of the copper powder at 570 Kelvin temperature. So dichlorodimethyl is formed. Dichlorodimethyl is formed. Now this is treated with the water, 2 moles. So 2 mole of the HCl goes out and we get a dihydroxydimethylsilane. Dihydroxy, you can see 2OH group here, dihydroxydimethylsilane. Noted down?
Yeah.
Now, n number of such molecule will undergo polymerization. You can see H with the one molecule, OH with the another molecule. So what will happen here? I will get here a long chain polymer of this. This is a repeating unit. We call that long chain is called as a silicon. Note it down.
Yeah.
Okay. Now I'll talk about the properties and uses of such silicons. Read on. Silicons are made up of short chain molecules. They are made up of short chain molecules. So these are oily liquids. They are chemically inert. They are chemically inert means they are resistant to oxidation. They are resistant to oxidation, thermal decomposition, or attack by organic compounds, attack by organic reagents. You can see that they are surrounded by alkyl group, non-polar compounds. They are surrounded by non-polar, they're water repelling. So these are water repelling. They're non-polar. So these are water repelling. They are heat resistant. So these are used to make insulating material. They're used to make insulating material. They are biocompatible. Biocompatible means they, if they are implanted in the human body, they will not affect our body. So they are used in surgical and cosmetic implants. They're used in surgical and cosmetic implants. Understood?
Yeah.
They are very good lubricants. They are very good lubricants which can work at a high temperature. Right? That is why you are using it in our engines as a lubricant, right? Understood? Yes or no?
Math.
Okay. Now am I going to ask you some questions, some multiple choice question practice now. My question is, I have a diamond, diamond. We have a graphite and we have an ethine. Tell me the hybridization of the carbon in each case. In diamond and graphite and in ethine.
For diamond will be sp3.
Diamond is sp3. Okay,
For graphite will be sp2.
good.
and for ethine also sp.
sp. It's a carbon-carbon triple bond. It's a sp. Here it is a double bond. So it is a in diamond it's a tetrahedral. So it is sp3. Okay, note it down. Note down.
Yeah.
Note it down.
Yeah.
No. We have dihalides of silicon SaCl2, GeCl2, SnCl2, and PbCl2. You have to arrange them in increasing order of the stability and explain why.
I'm not sure.
Yeah. See, I told you that as you go down the group, the plus 2 become more and more stable, right? So as you go down the group, the plus 2 state become more and more stable. But if I talk about the SiCl4, then the stability of the plus 4 is more stable in in the above. Understood?
Yeah.
Now, next question I'm giving you. I have an HI, HBr, HCl, HF. You have to arrange them in increasing order of their stability. Arrange them in the increasing order of their stability.
HF, HI, HCl, HBr.
Mac minimum, minimum, max minimum acidic,
HBr.
HF, then HCl, then HBr, then HI. Reason being, it's a HF, HCl. You can see that as you go down the group, the atomic size increases. As you go down the group, atomic size increases, right? The bond length will increase and the strength will decrease. I repeat, as you go down the group, the atomic size increases, bond length will increase and bond strength will decrease. So tendency to give H positive ion will increase. And that is why the acidic character decreases down the group. Understood? Yes or no?
Yeah.
Okay. Now another question is, I have a carbon dioxide, silicon dioxide, option A, option B, and option C, SnO2. Among these three, which is amphoteric in nature?
Silicon oxide.
No. Silicon oxide will give you silicic acid, right? SiOH whole 4. It's not a silicic acid. This will give you carbonic acid, right? This is the amphoteric. I gave you the reactions also, that with acid it is a base and with base it is an acid. Understood? Yes or no?
Understood.
Okay. One compound is, I'm giving you just one information. Pb3O4, right? This compound is a mixture of PbO and PbO2. This compound does not exist. It's just a mixture of PbO and PbO2. Okay, understood.
Yeah.
So that's all for this carbon family. Next time onward, we'll start with the basic concept of organic chemistry. Okay, right. So I'm ending session now. See you tomorrow, next week, and we'll start with the organic chemistry, basic organic chemistry. Right? Okay then. See you next week.